Chapter 2, Motion in One Dimension. Consider a car that is moving in a straight line from point P1 to point P2. The distance it travels is delta x, and it does so in a time delta t. So we're going to assume the car starts at P1 is equal to 20 meters. We'll just pretend this is the x-axis, say, and position P1 is at 20 meters relative to the origin. At time T1 is equal to 2 seconds. So it started at 20 meters at time equal to 2 seconds, and it got to position P2, which was at 92 meters, at a time T2 is equal to 6 seconds, 4 seconds later. And so its position change, right, its displacement is 92 meters minus 20 meters, or 72 meters. The number is positive, 72, and so that means the displacement was to the right in the positive direction. And the time it took to do that was 6 seconds minus 2 seconds, T2 minus T1, or 4 seconds. And so the velocity of the car is the change in position over the change in time, which is 72 meters over 4 seconds, or 18 meters per second. The fact that the velocity is positive indicates the velocity in my coordinate system was to the right. So if rather than the average velocity, if what we want to talk about is the instantaneous velocity, we have to talk about shorter time periods. And so we might say v instantaneous in the x direction is equal to the limit as delta t approaches 0 of delta x over delta t. In this case, we have a very short time period that we're looking at our velocity over, and then we can say the velocity is truly whatever it is, 2 meters per second, 18 meters per second, at that particular instant in time. This is the kind of thing that a traffic officer might be interested in, rather than the average velocity. And so the instantaneous velocity is similar to the average velocity, just with an infinitesimal time interval. So to further illuminate velocity and position and time, let's look at some graphs of position versus time, sort of x versus t graphs here. And we'll start by just considering a simple example of a car traveling at a constant 10 meters per second. And so let me pick a different color here, and let's draw a little graph here. Here's my position axis, and here's my time axis. And so we'll say the time is in seconds, right? And I'll have 1, 2, 3, 4, 5, maybe 1 seconds, 2, 3, 4, and 5. And then over here I'll have my position. I'll have 1, 2, 3, 4, maybe. And I'll call this 10 meters, 20 meters, 30 meters, and 40 meters. And this is our x in meters, right? And so once I have this, I can say, look, if the car starts at the origin, so it starts here, then after 1 second, it's gone to this position, which is the 10 meter position, right? And then after 2 seconds, it's at this position. And after 3 seconds, it's at this position. And after 4 seconds, it's at this position, right? And if I'm interested in its velocity, I want to know its change in position divided by its change in time, right? We keep saying the velocity, or at least the average velocity, is the change in position over the change in time. Well, what is that on this graph? Well, let's consider these two positions. Let's say where it is at 1 second versus where it is at 3 seconds, right? And so at 1 second, it's at 10 meters, right? At 3 seconds, it's at 30 meters, right? And so I can say, look, its delta x is just 20 meters, right? And its delta t here is 2 seconds, right? Because that's this distance here is the delta t, right? And so the average velocity, which is delta x divided by delta t, is just the slope of this line, right? And so that's equal to, in our case, it's 20 meters divided by 2 seconds, right? Or the average velocity is equal to 10 meters per second. And so on any position versus time graph, the slope is the velocity. And so we can learn a lot just by looking at some position versus time curves and asking ourselves, well, what's the velocity doing on this graph? And that's what we'll do next. So let's look at this graph now. What's this object doing, right? We can talk about it starts here and it ends here. We can say, well, we can talk about, we've already said we can figure out its average velocity. Its average velocity between the two endpoints is just the slope of this line here, right, connecting the two endpoints. But what's it doing in between? We can ask the question, well, what's the instantaneous slope right here? And it looks like something like that, whereas somewhere in here the slope is like that, and then over here the slope is flat, right, or fairly flat. What does it mean to have a flat slope, right? If the slope is horizontal this way, right, that means there's no rise over the run, and so delta x over delta t is 0 at this point, right? And so here is a car that's starting out fast and it's coming to a stop, right? That doesn't show up if we just write down the average velocity. That's just the final position minus the initial position divided by the time difference. And so we can look at this graph and say, oh, this is a car that's traveling fast initially and is steadily slowing down and it's coming to a stop. So this is another graph of position versus time. In this case, we've got a particle that's going from large position to small position as time moves forward. So what can we say about that? Once again, if we wanted to talk about its average velocity, it would be, let me just get a marker that works here. If we wanted to get its average velocity between the 2 points, we draw a line like this connecting the 2 points, right? And the velocity would be the slope of this line. We say the V average is equal to delta x over delta t for that line. But of course, that's not what the particle is doing at any instant. That just gives us an average. And once again, we can say, well, that's different than what the particle is doing, what the car or whatever the object is doing at any particular instant in time, right? First of all, the downward slanting slope, right, instead of an upward slope that we've seen in our previous graphs, means the velocity is negative, so it's traveling from the positive x to less positive or negative x, depending on how far it goes, right? And here, since the velocity initially is steep, right, we have a large negative velocity followed by a less negative velocity, followed by a less negative velocity, and maybe a horizontal slope, which would be a 0 velocity as the particle moves on. So this is a particle moving in the negative direction and slowing down. So now let's talk a little bit about acceleration. Acceleration is the rate of change of the velocity. And so we write acceleration as a is equal to delta v over delta t. Notice it's a vector in both cases. And the relationship between acceleration and velocity is the same as the one between velocity and position, right? If you remember, our velocity was equal to the change in position over the change in time, right? And so we can write the acceleration as just v2 minus v1 over t2 minus t1, and it's subject to the same arguments that velocity is subject to with respect to position. That is, if the two time intervals are close together, you get an instantaneous acceleration. If they're farther apart, you get an average acceleration. Right? And so the acceleration is the rate of change of the velocity. If we just want to know about it in the x direction, which is kind of what we're interested in most of the time, that doesn't look much like an x, and so I'll try to fix it. A sub x, the x component of the acceleration, is v2x minus v1x over t2 minus t1, or just the change in the velocity of the x direction divided by the time. So let's do an example here. This is a car traveling at 10 meters per second and accelerates to 40 meters per second in 6 seconds. And we're going to assume it does that acceleration at a constant rate, or we're just going to say, what's its average acceleration, right? And so we can say A average is equal to delta V over delta T, which is just V2 minus V1 over T2 minus T1, right? And that's just 40 meters per second minus 10 meters per second all over 6 seconds, we just assume it started at t equals 0, right? And so we can say this should be its acceleration. And so A average is just 30 meters per second over 6 seconds. Or we can say 5 meters per second. Sometimes we write that as 5 meters per second squared. When I think about it in my mind, I think of it this way. What this is saying is that the velocity is changing by 5 meters per second every second. That's what 5 meters per second is. If it was minus 5 meters per second, the velocity would be decreasing by 5 meters per second every second. And so you can write that as 5 meters per second squared, and the units, the SI units for acceleration are meters per second squared. We know that the dimensions for acceleration is length over time squared, right? And so in our units, it's the unit for length is meters and the unit for time is seconds, and so we get meters per second squared, and that's its average acceleration. Once again, that doesn't tell us what its acceleration is in any instant, but it tells us the average acceleration over that time interval. So let's look at some velocity versus time graphs to study acceleration, just like we looked at some position versus time graphs to study velocity. And so let me just draw a graph here like I was doing before. We'll just have another graph with time on the horizontal axis, and this time we'll have the velocity on the vertical axis. And we can once again just put some little hash marks in here. 1, 2, 3, 4, 5, 6. And then just 1, 2, 3, 4, 5 or something like that, right? And we can say if a car is traveling along this graph like this somehow, right? Then we can say, if we want to know what its velocity is between 2 points, we can say pick these 2 points. Maybe this is 10, 20, and 30 meters per second. And this is 1, 2, 3, 4, 5, and 6 seconds. We can say this guy occurs at 6 seconds, right? And this guy occurs at 1 second. And if I want to get a different color here real quick, I can say, look, the acceleration is the change in velocity over the change in time. And so I can say, A average right? And that's going to be this difference. That's my delta V divided by this difference, which is my delta T, right? And so that's going to be equal to the velocity difference is 30 minus 10, which is 20, divided by the time difference, which is 6 minus 1, which is 5 seconds. And so the acceleration, the average acceleration between those 2 points is 4 meters per second squared. That's my average acceleration. Didn't really write that well. That's my average acceleration. But we can see once again that the acceleration between those 2 points is not always the same, right? Here's my acceleration at the beginning. My acceleration somewhere in the middle is the slope along here, and my acceleration at the end. This is just like the position versus time graphs in determining velocity. The instantaneous acceleration is the slope of the line at a particular point. The average acceleration is the slope of the line between 2 points that are farther apart. And so when I look at this at different instants, I get slopes that are slower than the average and slopes that are greater than the average, and so they average out to the average acceleration. And so just depending on what I'm after, I need to either look at the instantaneous slope or the average slope between 2 points. Notice that this is very similar to how we did velocity from position and time. So here are a couple of graphs of position versus time for two different objects. This object has has a straight line, and this object has a curved line. And so we can look at this object and say it has constant velocity, right? What else can you say about the velocity of this object? Right? You should be able to say that the velocity of this object is positive because it's got positive slope. This object has an increasing velocity that starts maybe around 0 and steadily increases. And so if I were to draw a velocity versus time graph for each of these objects, this is the time graph, right? And this is velocity, right? This object's graph would look like this, right? Its velocity is constant and positive. So I don't know what its value is, but I know that it's a horizontal line. Similarly, this guy, right? If I had a time and a velocity here, this guy's velocity starts almost at 0, and so I would put it at 0 somewhere. I don't know what time it starts at, right? A little above 0, and it steadily increases. And so this guy's velocity might look like this, right? And so what can you tell me about the acceleration of this object, of object 1, say, of this object? Its velocity is constant, so this object has the acceleration is the change in velocity over the change in time. That's just 0 because its velocity is never changing, right? This guy's velocity is changing, and it looks sort of constant. And so this guy's velocity, all I can really say about it is that it's constant and greater than 0. So just by looking at a position versus time graph, I can tell a few things about the velocity and the acceleration, right? It's got a positive, its velocity is steadily increasing, so it's got a positive acceleration, and it's probably close to being constant. So let's try to go back to some equations in the acceleration of velocity. Let's start with the velocity. We have the equation for the average velocity, which is v average in the x direction is equal to change in position over change in time, which we've been writing as x2 minus x1 over t2 minus t1. We're going to rewrite those as x minus x naught. In other words, x is the final position and x naught is the initial position, over t minus 0. T is the final time, and we're just going to say our initial time is 0 since we can start our stopwatch whenever we want to, and that gives the average velocity is equal to x minus x naught divided by time. We can rearrange that and write it this way, where the final position is given in terms of the initial position and the average velocity. And so then we can take an example. We can do an example where the car starts at position x naught equals 25 meters, and it travels at 10 meters per second. We'll say it's its average velocity, but we could also say it's just traveling at a constant velocity. And then we can ask the question, where's the car at t equals 5 seconds? And so we just solve this problem, x equals x naught plus v average x times time, right? And that just gives us 25 meters plus 10 meters per second times 5 seconds, which gives us the final position is 25 meters plus 50 meters, or 75 meters. Right, and so that would be a simple position velocity equation and problem. So now we can do the same thing for acceleration. We can say the average acceleration here is the change in velocity over change in time, and again we're talking about the x direction, and so this is just v2x minus v1x over t2 minus t1. And again, we're going to do a little notation change, and we're just going to call the final velocity v sub x and the initial velocity v naught x, the 0 gives us a naught, over t minus 0. We're going to have our t1, our initial time, be 0, and our final time just be t. And that gives us vx minus v naught x over t. And we can rearrange that similar to the way we did the position velocity equation, as the final velocity is equal to the initial velocity plus the acceleration, or the average acceleration, times the time. And so then we can do a problem that has a given initial velocity and a given average acceleration, or maybe we'll just say it's got a constant acceleration of 2 meters per second squared, and find the final velocity. And so here we just grab that equation, we say Vx is equal to V naught x plus the acceleration times the time, and I've left my little subscripts off my acceleration there. and then I can say, well, that's just equal to 10 meters per second plus 2 meters per second squared times 7 seconds. And if I multiply all that out, that gives me 10 plus 14, or 24 meters per second. Right, that's my final velocity. So now we're going to talk about motion with constant acceleration. Right. Before we've allowed our acceleration to be anything, it can change or it can not change, just like our velocity. But for a lot of examples, it's making an approximation of constant acceleration, that is to say the rate of change of velocity is constant, is a pretty good approximation. What it means is that in all of your velocity versus time graphs, right, your curves are straight lines. These should be straight lines, right? There are no curves like this. That doesn't happen. If your acceleration is constant, it means your slope of your velocity is a straight line. I tried to make those straight. When that happens, you get these two the same equations we've had before, x equals x naught plus v average x times time. The velocity can still change when you have a constant acceleration. Now we have our equation for our acceleration, which is vx equals v naught x, the initial velocity, plus the acceleration times the time. This time I didn't indicate it's the average acceleration, because our average acceleration is the same thing as any other acceleration. They're all constant. In the case where you have a constant acceleration, your average velocity, the same guy we talked about up here, is equal to the initial velocity plus the final velocity divided by 2. So if I have a car on a ramp, if I say v naught x is equal to 10 meters per second, right? It enters an on-ramp at 10 meters per second, and its final speed as it enters the highway, leaving the ramp, is 30 meters per second. Then I can say its average velocity is 10 meters per second plus 30 meters per second divided by 2, or 20 meters per second. This kind of statement is only true if the acceleration is constant, that is to say if it's steadily increasing from 10 meters per second to 30 meters per second. You can imagine a car that goes at 10 meters per second the whole time and then accelerates at the very end to 30 meters per second. Then its average acceleration would be much closer to 10 meters per second. Its average velocity, would be much closer to 10 meters per second because it spent most of its time there. So it's only in the case where you have steadily increasing velocities or constant accelerations where this equation, initial plus final divided by 2, gives you the correct average acceleration that you want. We use this equation, the average velocity is the initial plus the final divided by 2, in future problems and to derive certain equations that are very useful in solving some of our kinematics problems. So we're going to start with one of the equations we had last time, which is this one. This was just a rearranged equation for our definition of acceleration in terms of velocity and position, but now we've got a constant acceleration. All right, and so we're going to start with this equation and we're going to add v naught x to both sides, and so that gives us v naught x plus vx equals 2 v naught x plus the acceleration times the time, right? And then we're going to divide both of these equations by 2, which we're free to do. And that gives us v naught x plus vx divided by 2 is equal to v naught x plus 1/2 a times t. Right? Well, this equation here, this piece of it here, right, is just my average velocity, right? And so this is vx average, or v average x, let me say it that way. Average x is equal to v naught x plus 1/2 times the acceleration times the time. And I can go back to my earlier equation for position and velocity, and I can say x equals x naught plus v average x times t. Right? This is the equation that we derive from the definition of the average velocity. And what I'm going to do is I'm going to take this thing, right, and I'm going to put it in there for the average velocity, right? And what I get is x equals x naught plus, and then this thing, v naught x plus 1/2 at times t, right? And so this leads the equation down here, x equals x naught plus v naught x times t plus 1/2 a times t squared. And this equation, let me clear that x up a little bit, right? This equation gives us our final position right here in terms of our initial position, our initial velocity, and our acceleration. And that's a pretty useful equation for problems where we know the initial conditions. We can go directly from initial position, initial velocity, acceleration to final position. And so I'll do an example of that here. So here's a problem. A car starts from rest and accelerates at 2 meters per second squared. How far does it travel in 7 seconds? And so there are a few clues in here. First of all, since it says the car starts from rest, that tells us that v naught x is equal to 0. We don't care where it starts from because we want to know how far it travels. And so what we're really being asked for is x minus x naught. That's what they want us to know, right? How far does it travel? What's the difference between its final and its initial position? We usually just pick x naught equal to 0. Sometimes you can't, but in this problem you can. And so then we can just go to our equation and we can say, look, x equals x naught plus v naught x times time plus 1/2 times the acceleration times time squared. And when we start filling stuff in, we get a 0 plus, since it started from rest, we get a 0 times time plus 1/2 times 2 meters per second squared times 7 seconds squared, right? And so that gives us the distances traveled, or its final position in this case, is 1/2 times 2, which is 1, times 7 squared, which is 49. The second squared cancel, and we get 49 meters. Right, let me clean that up just a little bit. They could have also asked us, what was its final velocity, right? And we get Vx is equal to V naught x plus the acceleration times the time, which is 0 plus 2 meters per second squared times 7 seconds, right, which is 14 meters per second, right? What was its average velocity? We could say its average velocity is equal to the initial velocity plus the final velocity divided by 2. The initial is 0, and so its average velocity is just 7 meters per second, right? Because the final velocity was 14 meters per second. That's what we decided here. And the initial velocity was 0, and so that gives us an average velocity of 7 meters per second. Notice that we could have also calculated the distance it traveled this way. We could have said the average velocity is 7 meters per second multiplied by the 49 seconds, the 7 seconds. And we get the exact same answer we got by using this one formula up here.